Hi, I'm Tianqi from Tsinghua University, and today I will talk about the meta problem of how do we prove circular bonds. This is a joint work with Lijie and Chen. So let's get started. I will first introduce the background of our work, including the natural proof barrier, the black box natural proofs, and Williams' equivalence between non-deterministic circular bonds and constructive properties. I will then show you our main theorem, which says that black box constructive proofs are unavoidable. And I'll give you some intuition of how the theorem is proved. I would very much like to talk also about the main technical ingredient, which is a smooth, strong, and locally decodable PCP, but I will not go into this since I have no time, but you can check the paper for details. Finally, I will present some open problems. Okay, the main question we are curious about in this talk is, how do we prove circular bonds? Let us take for example that we wish to prove Z does not have polynomial size circuits. How do you do that? You suppose that we have this whole space of functions here, and we have the language Z, which I marked green here, and we have some of the functions in this space computable by polynomial size circuits. I marked these functions red here. So what do we do to prove the lower bound? One natural way to think of is we cut a line, such as the blue line here, that separates the green points from the red ones. If indeed the set, this green point is in the blue area, and there's no red point in the blue area, then we can get set is not contained in P/poly. But this is not over. For the sake of our Stone Age human brains, it is much easier to think of a blue line if it satisfies two additional properties. The first is largeness, saying that this blue area is not too small, and the second is constructivity, that says that this blue line is not too simple, it's not too complicated. Why is that? Well, you don't want the line to be as complicated as this one, right? I can't imagine how we can work with such a stuff. And also, if the blue area is too small, like this red oval here, then it's just too ad hoc for us to argue with. As a natural blue line come up with some human should mostly satisfy these three properties: usefulness, largeness, and constructivity. So this leads to the formal definition of natural proofs by Lijie and Lijie in 1994. Throughout this talk, we assume that C is a typical polynomial size circuit class such as P/poly, NC1, TC0, or ACC0. Here I write the blue line as a property P, which is a subset of all Boolean functions. The functions in the subset corresponds to the blue area here. We say it is natural against some circuit class C if it satisfies the three properties usefulness, largeness, and constructivity. First, usefulness. It says that no red points are in the blue area. This means that for any language L in the circuit class C, there exists infinitely many input lengths n, such as Ln is not in the property P. Here Ln means the language L restricted to this specific input length n. And of course, since we are proving lower bounds, we need at least one language, say the language set, is in this property. So we should have the property Pn to be non-empty. Second, largeness. This means that the property Pn is not only non-empty, but it is also large. It contains at least 1 over poly n fraction of the functions. The original definition by Lijie and Lijie here is 1 over poly 2 to the n. But this is not very essential, and 1 over poly n is much more convenient for us. So let's stick to this setting. And last, constructivity. Blue line is simple. This means that given the truth table of a function as input, here the input length is should be the length of the whole truth table, which is 2 to the n. This is very important. So remember, keep this in mind throughout this talk. Okay, given the truth table as the input, we can decide whether the function is in the property P in polynomial time. Here I emphasize again the input length is 2 to the n. So by polynomial time, we mean poly 2 to the n time. So this is the formal definition of natural proofs. If you can't remember the formal definition, it is completely okay. You just remember that by largeness, we mean the blue area covers at least 1 over poly fraction of the whole space, and by constructivity, we mean that deciding whether a function is in the blue area can be done in poly the length of the truth table time. Okay, as we mentioned before, a natural proof is the most intuitive way of proving a lower bound. And indeed, most lower bounds in the literature satisfy these 3 properties. But unfortunately, the drawback of being natural is being simple. The seminal work by Rasper and Rudich showed that natural proofs are just too intuitive and simple for us to prove superpolynomial size circular lower bounds. So if we want to prove something like Z is not contained in P/poly, we must go beyond natural techniques. To be more specific, they show that if strong pseudo-random functions can be computable in C, then there is no natural properties useful against C. And we believe such strong pseudo-random functions to exist in very weak circuit classes such as formulas or even TC0. So this means that if we wish to prove superpolynomial size lower bounds for even such weak circuit classes, we will need to use some non-natural techniques. But how? How can we overcome this natural proof barrier? Since usefulness should be inherent for proving a lower bound, we can only think of getting rid of either largeness or constructivity. By avoiding largeness, we are trying to say that specific functions like Z are hard for special reasons, so we can't expect a property to work for a vast proportion of functions. On the other hand, if we try to avoid constructivity, it means that the lower bound, such as Z is not contained in P/poly, is hard to prove because human reasoning is in polynomial time. We need to go beyond such primitive reasoning to prove the lower bounds. But still, the question remains: which of the largeness or constructivity should we avoid? Williams gave an answer to this question about 10 years ago, saying that proving a superpolynomial lower bound actually implies a constructive but not large property against C. In fact, it built an equivalence between Nx is not contained in C and constructive properties. Here, Nx is non-deterministic exponential type. So it means that to prove a lower bound such as Nx is not contained in C, we cannot, after all, get rid of constructivity. But now the question comes. We already know that constructivity cannot be avoided, but how strong should the constructivity be? Is it the case that even stronger notions of constructivity are unavoidable? So this comes to the notion of black box constructivity introduced by Fan, Lee, and me in the last year. The original definition of constructivity requires that whether the function is in the property is decidable in poly 2 to the n time, that is polynomial to the truth table length. Maybe we can be much more ambitious. We can ask whether it is decidable in probabilistic polylogarithmic time, that is poly n time. This is I say polylogarithmic because this is polylogarithmic to the truth table length. Now, of course, the constructing algorithm cannot take the whole truth table as input, but it can only have an oracle access to the function f. There are some technical details for this definition. Actually, we must first generalize the properties to promise properties, which is 2 sets Pn yes and Pn no, and the algorithm is only required to distinguish the function from being Pn yes or Pn no. If the function is in neither of them, then the algorithm can output anything. We just don't care. That is, intuitively, instead of having a blue line separating the red points and the green points, we have a white-blue strip here, and the algorithm can output either yes or no on this strip. Here I use an example to explain why this gap between Pn yes and Pn no is useful. Suppose that you are given a sequence of 0, 1 bits, and you are asked to decide some properties related to the proportion of 1 bits in the sequence. Suppose first that you are required to decide exactly whether there are more than half of 1 bits. then you can't do it very efficiently by summing only a few bits, right? You must read almost all the bits. But if I only ask you to distinguish if the number of lines is more than 2/3 or if it is less than 1/3, and I don't care about your answers if it is in between the thresholds, then you can of course answer this question very efficiently by a simple sampling. So this is the difference. So our actual definition of black box constructivity is, for a promised property, if a function f is in Pn yes, then our algorithm accepts with some large probability. And if the function is in Pn no, then the acceptance probability is small. And we don't have a guarantee on the acceptance probability if it is in neither Pn yes nor Pn no. Okay, this may be a bit technical, but the key point is just the algorithm runs in probabilistic poly n time instead of a much slower poly 2 to the n time. Why is the black box constructivity seemingly much stronger than the original one? Here I give you another view. Let us first consider the original constructive property useful against C. You can actually view it as some sense of analysis algorithm for C. It reads the truth table and tells you something non-trivial about the circuit class C. And what Williams' equivalence tells us is that such an analysis algorithm is actually equivalent to proving circuit lower bounds. Similarly, we can say that a black box constructive property can be viewed as some super efficient property testing algorithm for C. It tells something about C by only querying a few bits about the function. This is some sense of property testing. So this certain form of property testing algorithm seems to be much stronger than the slower analysis algorithm. But is it? In this paper, we give surprising answers to this question. Okay, it at least surprises us at first, that this black box constructive property, and also this certain form of property testing algorithm, is also equivalent to circuit lower bounds. So all these are all equivalent. And our intuition that black box constructivity is much stronger should be wrong. They are actually equivalent. Okay, so here is the formal theorem. Nx is not contained in C implies a black box constructive property useful against C. And combining with Williams' equivalence, all the following are equivalent. Nx is not contained in C, the existence of constructive property, and the existence of black box constructive property. This tells us that to prove circuit lower bounds, we will have to be able to show this sense of super efficient property testing algorithms for the circuit class. It also tells us that if we have a constructive property, which is in time poly 2 to the n, we can generally bootstrap it into a poly n one. Good. But before we go on to the overview of the proof, let's first say a word about the randomness in the definition. You may wonder in the definition of black box constructivity, why is the algorithm probabilistic? We prove that this randomness is actually essential, in the sense that deterministic polylog time constructivity does not exist. We also have other related results in the paper, such as the bootstrapping result on the black box constructive and also large properties. You can read our paper for more details. Okay, for the rest of the talk, I will give you some intuition of how the equivalence is proved. Let's first start from Williams' result in 2013. Nx is not contained in C implies the existence of a constructive property useful against C. The proof goes in two steps. First, Williams proved that Nx lower bounds implies some sense of Winnie's lower bounds that I will explain shortly. Then Williams showed a constructive property from this Winnie's lower bound. So what is this intermediate Winnie's lower bound? It says that there is an Nx verifier V. Let us say that it decides the language L, such that for any circuit family C in a circuit class with a pair of inputs, there is an infinite sequence of inputs x1, x2, x3, such that for all such xi, it is in the language L, but this truth table of Cxi with xi as the first input fails to witness xi. That is, Vxi with the truth table rejects. So this lemma actually says that Nx does not have small circuits, implies that Nx verifiers do not accept simple witnesses. This is in fact an equivalence. The other direction of this lemma is just a well-known easy witness lemma. I will not dive into this because it is a bit too technical, and we will only use it as a black box. But the second part is much more important for us, so I will say a bit more here. In this step, we start from Nx verifiers do not accept succinct witnesses, and we want to construct the constructive property useful against C. The property itself is quite simple. We just take a bad input x bad. By a bad input, that means that all the witnesses of it are of large circuit complexity, and we simulate the Nx verifier with the truth table of the function as the witness y. That is, you output this Vx bad and the truth table of f. This property is of course constructive, but why is it useful? Suppose it is not. Then there is a function f in the circuit class C, but it is accepted by the property. This means that this function f is a witness for x bad, but it is of low circuit complexity. This leads to a contradiction. There is a technical issue here of how do we find such a bad input x bad. One way to do this is simply take the bad input as advice. This is a bit too technical. We just forget about it here. So here's the proof. The running time of the property is the same as the Nx verifier, so it is polynomial in the truth table of f. Now, our goal is to make it polylogarithmic. How do you do that? As some of you may already figure out, the answer is to use probabilistic checkable proofs. Let me recall here that a PCP verifier for an Nx language takes the input x and an internal randomness r and access to a proof oracle pi and runs in poly x time. That is, it only makes poly x queries to the proof oracle, although the proof oracle itself may be of exponential length. And we have, for any x in this language L, there is a proof oracle such that the verifier accepts with certainty. But for any x not in the language, no proof oracle will make the verifier accept with probability more than a third. Now we follow the ideas in the previous slides, but use a PCP verifier instead of just an Nx verifier. We simulate the PCP verifier with the same bad input x bad and the function as proof oracle. Then the running time of this property will become polylogarithmic to the length of the truth table, which is the length of the proof oracle. So this is indeed a black box constructive property. To make the property further useful, we now need the assumption that there is a PCP verifier whose almost witnesses are not too simple, say not representable by C. By almost witnesses, we mean here the proof oracles that make the verifier accept with probability close to 1. So here's the outline of our proof. We start from Nx is not containing C, and our goal is a black box constructive property useful against C. We still use the first step in Williams' proof, which gives us a witness lower bound for from the Nx circular lower bounds. And the previous slide tells us that almost witness lower bounds for PCP verifiers implies black box constructive useful properties. But there's still a gap in the middle. The bottom one looks to be stronger than the upper one, since PCP verifiers are special cases of Nx verifiers and almost witnesses are a superset of witnesses. They only require an acceptance probability to be close to 1 instead of exactly 1. But actually, if we use the specific PCP with special properties, in particular a smooth, strong, and locally decodable in the circuit class C, we can make this implication true. And we are indeed able to construct such PCPs. The construction is so technical that I will not go into details. But the point is, with the construction of such PCP and this observation that such PCP system preserves witness lower bounds, we are done. Okay, finally, I will conclude with two related open problems. First, does such equivalence also work for superpolynomial-sized circuits? And can the equivalence preserve the circuit complexity? Currently, if we want a black box constructive property against C circuits of Sn size, we must rely on the lower bound assumption against C circuits of much larger circuit size. Can we improve this to say tilde Sn? This may allow us to build much finer equivalence instead of just saying polynomial size. In our current technique, this overhead comes from the middle part, this weakness lower bound to PCP almost weakness lower bound. So it will be interesting if we can remove such overhead. Okay, that's all. Thank you very much.